Hello there, this is Sophia from Pineapple Tuition. I've nearly lost my voice from all the teaching I've been doing this week. This is your Chemistry Paper 1 Masterclass. I'm going to try and go through the key bits of Chemistry Paper 1 for you so that you are ready and prepared for the exam this week. So in Chemistry Paper 1, you have 5 topics that you need to be revising. The atomic structure and periodic table, that's all the basics of how an atom is arranged. We'll have a look at that in just a second. We're going to talk about bonding, structure and properties of matter. So I've got a nice summary of that for you here as well. The quantitative chemistry is where your calculations come in. And then you've got your chemical changes, so your acids and base stuff goes into that topic. And then you've got your energy changes, which is your endothermic and exothermic reactions, which we'll look at in a moment. So first idea here then, you should know the basic structure of an atom, where in the nucleus in the middle you have the protons and the neutrons. They make up the nucleus, and that is what gives you the mass number. And when you have an element in the periodic table, the mass number is the big number that you are looking at in the periodic table. Okay, it's like taking the nucleus, picking it up and putting it onto the scale. So the protons and the neutrons make up your nucleus. The other number, which is the atomic number, is the smaller number. So with beryllium here, it's 4. And that smaller number tells you 2 things. It tells you how many protons there are in the nucleus. So there's 4 protons in this case. But also, because the protons, remember, are positively charged, it also tells you the number of electrons that are in the atom, because electrons have a negative charge. And just remember that the positive charge in the nucleus is equal to the negative charge of the electrons. So number of protons equals number of electrons. So you need to be able to draw the electronic structure of atoms that you are given. And so you might be given, for example, well, we've got lithium here. We've got the small number 3, which means that there are 3 electrons in lithium, right? And so that atomic number tells you you've got 3 electrons. And the way we arrange the electrons in the shells is the first shell can have a maximum of 2 electrons. So that's the closest to the nucleus here inside. The second shell has a maximum of 8 electrons, and the third shell also has a maximum of 8 electrons. So when you draw the electronic structure, what you will do is you will, let me just get a little thing here. You'd usually use crosses to show it. So where we've got lithium, we've got 3 electrons altogether. So in the first shell here, you would put your 2 electrons, because that's the maximum it could take. You've got 3 altogether. We've got 1 more electron, so we'll put that out on this second shell here. And then you'd write lithium in the middle, so you know that's what you're talking about. If we do a more complicated one, let's do carbon even down here. Carbon's got a small number here of 6, which tells us we've got 6 electrons altogether in carbon. If in our first shell we can only have 2, well, the 2 would go in this first inner shell, put carbon here. And then we've got, if you've got 2 electrons, we've got 6 that we have altogether. And so the other 4 would go 1, 2, 3, 4, and we'd fill up that shell to 8. And when you fill up to 8, then you start the third shell on the outside, which is why you've got the bigger ones down here. So you might want to pause the video and then have a go at drawing these out to make sure you know how to do it. And what I'm going to do is get rid of these annotations like this, and I'm going to show you what the answers should be. So the first one here, if you're going to let me click through. Oh, no, you're not going to let me do that. Okay, so now I've got the correct slide up, and I can show you. Hopefully you paused the video and had a go at drawing these out. When you're drawing them out, okay, with the crosses like I showed you previously, what you want to also be able to do is write down what we call the electronic configuration. And in this case with lithium, if you remember, we put 2 electrons on the first ring. So the first number here is going to be 2. The third electron was on the last ring, on the outside ring here, and that's where you get your 1 from. And your answers here, I'm just going to show you, there's a pattern here, look, always 2 in the inner energy level, okay, or inner shell. And so you look at the pattern as the atoms get bigger, you will see here we're adding the number of electrons as we're going through. Okay, so check what you've got and make sure you're comfortable with that. Now, the other thing to remember is the group number. So the groups, remember, in the periodic table are the columns going downwards. How does that relate to electronic structure? Well, if something is in group 1, it tends to have 1 electron in its outer shell. If something is in group 2, it tends to have 2 electrons in its outer shell, and the same for group 3, 4, etc. And so the group number is the same as the number of outer shell electrons. Okay. Okay, we need to know about this atomic model. And so what you have is a number of scientists that came up with different models to show where we got to today, where we have the protons and neutrons in the nucleus, and you have the electrons whizzing around the outside. So we've got a kind of timeline, if you like, where we've got John Dalton here, who said that tiny spheres cannot be divided. Okay. J.J. Thomson was the next scientist who then said, he discovered the electron. The experiments he did were the plum pudding model, and this was where spheres of positive charge with negative charges are spread evenly throughout the atom. Okay, so that's a plum pudding model, was J.J. Thomson. Now, Rutherford, Geiger, and Marsden did the alpha particle scattering experiments, and here they came up with the nuclear model, where they've said the mass of the atom is concentrated in a nucleus that has a charge with electrons orbiting around it, right? So now we're moving towards the model that we have now. Nextly, we have Niels Bohr, and he said or discovered that electrons orbit the nucleus at specific distances in fixed energy levels or shells. Okay, so that was Niels Bohr's discovery. And he said also, when electrons change level, there is energy that is given out. Okay, and that can be used for useful things. The positive charge of the nucleus could be subdivided into particles of positive charge. So you've got this 2 types of subatomic particles in the nucleus. One of them is the proton, which we now know has a positive charge. And James Chadwick more recently provided evidence that there were neutrons within the nucleus as well as the protons that we previously knew about. So the next topic here is structure and bonding. So looking at topic 2, you've got to know about ionic, simple covalent, giant ionic. Let's do it in order. Ionic bonding and giant ionic. So the first left-hand side of the screen. You've got simple covalent molecules, you've got giant covalent structures, and lastly, you've got metallic bonding. Okay, so if we start off with ionic bonding, again, this is a bit of a gap fill, so you might want to pause the video and fill in the gaps as you go along. But ionic bonding happens between a metal and a non-metal. And so the reason that they're so strong is because they have opposite charges. Metals are usually positively charged and non-metals are usually negatively charged. If an atom loses an electron, we're giving away that negative charge, and therefore it has a positive charge. So think of the electron like a donut, right? You're holding the donut in your hand. If you give away that donut that has a negative charge, you are now positively charged. You've given away that negative charge. If an atom gains an electron, it has a negative charge. So again, the person who takes that donut off you has now got the negative charge, so they are now having a charge of -1. The next one, which one is it going to go to? Here we go. So you've got giant ionic structures. So these are things like sodium chloride. So this is like salt, right? And we can describe these giant ionic structures. You've basically got lots of positively charged and negatively charged ions that are arranging themselves together to form a bigger structure, which we call a giant ionic structure. Think about giant, think about big. So giant ionic structures like sodium chloride make large structures that we call lattices. Okay, and so they have a very high boiling point and melting point because you've got so many particles, ions there together that are positively charged, negatively charged, all sat next to each other. So you've got positive, negative, positive, negative, positive, negative. That's how you get the green and the purple kind of image down the bottom here. And because they have these strong ionic bonds, the positive and negative attract each other so much, that makes the melting point and boiling point really, really high, because it means you need a lot of energy to break those bonds between them. Now, they can conduct electricity when we dissolve them in water. So think about, again, a teaspoonful of salt that you've dissolved in water. or they can also conduct electricity when they are molten or melted down. And this is a really useful property to use when we're looking at something like electrolysis, which we'll have a look at in a few moments. Now, hopefully we'll go to simple covalent now. So ionic bonding, remember, is when you have electrons that are given and donated, donated and taken. So electrons are given completely or picked up by another atom. Whereas if you've got covalent bonding, this is the kind where sharing is caring. See, for covalent, we are sharing electrons. And here, covalent bonding happens between a non-metal and a non-metal, two non-metals. In this case, electrons are shared with simple covalent bonding, and it says most small covalent compounds like oxygen and water are gas and liquid at room temperature. So oxygen at room temperature, think about the oxygen around you, it's a gas. Water at room temperature, got a glass of water on the table, it is going to be a liquid. The reason for this is because the forces between the molecules are weak, but the covalent bonds are strong. Okay, so we do have quite strong covalent bonds when these electrons are shared. Now, the larger the mass of a covalent molecule, the higher the boiling or the melting point. Okay, so the bigger the mass of the covalent molecule, the more energy you need to boil or to melt it. Okay, similar idea to the giant ionic, but don't get them mixed up. Now, the next one, let's see, we're going to go to giant covalent. Now, again, these are bigger molecules that still are sharing electrons with each other. So again, giant covalent, you're looking at stuff like diamond, stuff like graphite, stuff like, there's one more called, I think graphene might be in here as well. Or Buckminster fullerene comes up sometimes as well. So giant covalent structures act differently to simple small covalent structures. So think about diamonds, it's the hardest thing known to man. Diamond's got a really, really high melting and boiling point. It has strong covalent bonds. Now, diamond cannot conduct electricity because there are no free electrons that are floating around. Okay, the electrons are all shared to form those covalent bonds. Graphite and diamond are both made of carbon. Okay, so these are molecules that are large, giant covalent structures made of carbon, and graphite is soft because it has layers of like sheets, if you like, of carbon atoms covalently bonded together, and in between each flat layer you've got weak intermolecular forces. Remember that language, weak intermolecular forces, and that means that graphite ends up being soft. Graphite can also conduct electricity here because there are free or delocalized electrons that can move about between these layers, right? Lastly, you have metallic bonding here for topic 2. Now here, where metals generally like to lose electrons to form positive ions. So think about sodium. Sodium is a metal and forms Na+, a positive ion, because it loses an electron. These electrons being lost are all donated to the sea of electrons, and this is what makes metals conduct electricity really well, because those delocalized electrons can move around. So let's have a look at the next idea of what we got. Question said, what are some properties of metals? They have a very high boiling point and very high melting point. That's what MP and BP is. They are malleable, okay, which means they're soft, and they're ductile, which means they can be shaped into different shapes. Okay, we need to be able to use our periodic table, and we need to be able to find, first of all, the relative atomic number. Okay, and that's the big number when you look at the periodic table, and that will give you the relative atomic mass of a particular element. Now, on the list in front of you here is you have a list of compounds. Now, these compounds have more than one element in them, so we need to find this MR, which is the relative formula mass of a particular compound. And the way that you do this, again, I'll just put a note on here so you can see how you do it. I'll give you one as an example, is that if my pen starts to work, here we go. So carbon dioxide. Now you should know that the formula for carbon dioxide is CO2. This tells us that we have one atom of carbon and we have 2 atoms of oxygen. Remembering this little 2 is stuck to the oxygen, just the oxygen. Okay, you can't change that 2, by the way, just like any of these little numbers, you cannot change them. When you are balancing equations, the only thing you can do is put a big number in front. Now, with carbon dioxide, we said 1 atom of carbon and 2 atoms of oxygen. The relative atomic mass of carbon is 12. The relative atomic mass of oxygen is 16. And the relative atomic mass of oxygen, we've got 2 oxygen, sorry, so you've got another 16. You add all those together and that should give you 44. Okay, that is the relative formula mass for carbon dioxide. Now what you want to do now is pause the video and go through a couple of these here and check that you are able to find the relative formula mass of each of these compounds on here. Not forgetting, again, if we go to the bottom one here to help you, sodium, there's 2 sodium atoms here, there is 1 carbon atom here, whoops, and there's 3 oxygen atoms here. That little 3 belongs to the oxygen. So when you do your adding up, make sure you're looking for the big number on the periodic table and selecting the correct numbers, because that was an error that a student made this week with me, and find out what the relative formula masses are. So pause the video now and find out what they are. I'm going to get rid of these annotations. Where are you at? Come on, menu. Perfect. So we get rid of you. Okay, so what I'm going to do is show you what the answers are and see how you got on. So if I just run down, it lets me do it. Here we go. So check the answers that you've got and make sure that you agree with what is on the screen. Okay. Right. Equations that you need to remember for the quantitative chemistry. If you are a combined science student, you're doing the trilogy course, you need to know this triangle here at the top. You need to be able to use, put the mass at the top here, and the way you find the mass is you take your number of moles and you multiply it by the relative formula mass. If you're a higher tier student, you should be able to do mole calculations. And separate science have got another set of formulae, which I'll show you in just a second. The units you're going to use for mass is in grams. Moles are measured in moles. And then the relative formula mass is grams per mole. So this -1 means grams per mole. You can also write it G/MOL, but this is probably the more fancier way to write it. So you should be able to, again, use this triangle. You cover up the thing that you want to find out. So if I want to find out the number of moles, I cover up the number of moles with my finger, and I've got left mass. You've got an invisible division sign here, divided by the relative formula mass. That's how you get the first one up here. And again, for the rest of the triangle, you should be able to cover up what you're looking for and then look at the other 2 things that you've got. And so mass divided by moles, mass divided by relative formula mass, or moles multiplied by relative formula mass. Remembering that 1 decimeter cubed or 1 decimeter cubed is 1,000 centimeters cubed, which is the same as a liter. You should be able to calculate the concentration of a substance in grams per decimeters cubed. What you do is you get the mass of the solute in grams, okay, and you divide it by the volume in decimeters cubed, remembering that decimeters cubed is the same as a liter. To make it easier, you've got a triangle down the bottom here to manipulate this formula, so we can have a look at rearranging it to find different parts of this actual equation. Remember to do your conversions, particularly at higher tier. You will be expected to be able to convert from centimeters cubed to decimeters cubed, okay, between these 2. Right, if you are separate science now, not only do you need to know what I've just spoken about to do with the moles, you also need to work out down here the percentage yield. Now this is the actual yield, what you get from the reaction, divided by, in theory, how much should we get as a prediction. You multiply it by 100 to get the percentage yield. This is the same as if you get a mark in a test. If you get like 5 out of 20, if you actually got 5 marks, divided by, in theory, you should have got 20 marks altogether. 5 divided by 20 multiplied by 100. Use your calculator to do that. Concentration, we've already looked at on the previous slide. Remember, this slide is separate science only. Excuse me. Your gas volume is, again, your volume at the top here, the amount in moles in 24 down here. And again, same way of using the triangle, cover up what you're looking for. And then you've got the other two values there, invisible division, invisible division, invisible multiplication sign. Conversion, 1 decimeter cubed is the same as 1,000 centimeters cubed. And then concentration, I think we've done this one before. No, if you're given in a question, moles, concentration and volume, you need to put those together and manipulate them. Your triangle is here, okay? And down the bottom also, you've got your atom economy calculation. Now, with your atom economy, you need to be able to figure out the mass of atoms in the product that you want divided by the mass of the atoms in the reactants, and then multiply that by 100, okay? And practice some of these calculations so that you are confident using them. Now, I'm gonna pause this just a second. Okay, when you are doing mole calculations, you need to be able to calculate the number of moles. And remembering here, if I pop my pen up here again, I'll give you this first example here. Come on, pen, wakey, wakey. No, we're gonna go back to sharing. Here we are, lovely. Right, so when you're calculating the number of moles, if you remember, the number of moles is gonna be your mass in grams of what you've got, divided by the relative atomic mass of the element or the formula mass of the compound. So you can put MR of the element or compound. Okay, and so what you would do is, these are quite nice, quite simple ones here. If you've got sodium, if you look at the relative atomic mass from the periodic table, just look it up. The bigger number you're looking for is 23, and we're given 13 grams of that. What's the number of moles? So what we do is you take your mass, which is 13 grams. You're going to divide that, squeezing it in here, by 23. Okay, and when you put that into your calculator, you should get, put it in now, what we got, 13 divided by 23. I'm getting 0.565, but we asked for the answer in two decimal places. So your answer here will be 0.56 moles. Okay, squeeze it in there. So if I go to here. Okay, when you are doing the mass calculations here, so again, I've got my pen ready here for you. You're trying to calculate the mass here. So just a reminder now, if you're looking for the mass in grams, okay, what you're going to do is you're going to take the number of moles, okay, and you're going to multiply that by the relative atomic mass of the element or formula mass if it's a compound. So here we've got 2 moles of lithium. So if I go to the periodic table and I look up lithium, I'll find the relative atomic mass of lithium is 7. So in this case, our simple calculation here is 2 moles times 7, the relative atomic mass of lithium, and that should give us a mass of 14 grams of the lithium. So that's how you do your mass calculations. Now, in a moment, when I get to the end of this slide, I will get you to pause the video to check your calculations of these, and then you can check what you've got to make sure you're getting it correct. So, working out the concentration in grams per decimeters cubed of these solutions. Look at the units here. This is your clue on how to do this if you don't remember how to do concentration. Grams per decimeters cubed. So how many grams of my solute have I got? In this case, 68. Okay, 68 grams. Divide it by the number of decimeters cubed. So you've got 4 decimeters cubed here. 4 decimeters cubed. And if I put that into my calculator, divided by 4, go, that should give me 17, whoops, I'm scribbling it on here, 17 grams per decimeter cubed. Okay, so now what you can do, I've given you an example of each one. If you pause the video and then make sure you can do each of the calculations, and then you can come back and check whether you've got it correct or no. Okay, so the answers here, I'll pop these up for you so you can now have a look and check to see if your calculations are correct. Here they go. right? Remembering for every single one of these answers, look, I've put the unit down that I've calculated. Okay, if it said 2 decimal places, I've done it to 2 decimal places. Make sure you do that in the exam. Okay, right, a required practical. Let's go through these steps here. You are required to explain how to make a salt from an insoluble base. So the first thing you're going to do is you're going to put some acid with the required volume of acid with a measuring cylinder. Tell me the equipment you're using, and you're going to add the weighed solid in small portions while stirring every time. So you're adding the solid, adding the solid, adding the solid. You're going to have to wear safety goggles for this procedure, and the mixture may be heated to speed up the reaction. When there's no more of the solid dissolving, it means all the acid is neutralized and there should be a little excess solid. So you'll see some solid bits in the bottom. Now, you're going to filter the solution to get rid of any excess solid. You're just interested in the stuff that is actually dissolved. And so when you filter that solution, only a solution of the salt is left behind. When hot concentrated solution is left to cool and crystallize, then you leave the solution that's hot and concentrated to cool down and crystallize. After crystallization, what you'll see the crystals formed, and then you can dry them with filter paper. Now, if we heat the solution, that will get our solvent to evaporate much faster and dissipate into the air. Heating a solution until all the solvent is evaporated, the language we use is it's heated to dryness. Okay, till all the solvent has evaporated into the air. So next idea is electrolysis. This is a very, very common topic to come up. There are specific examples that you need to know. Okay. And so when you get your electrolysis question, what you'll have is you've got a setup like this where you've got a current supply at the top, you've got electrons that are moving around, and what happens with the electrons is you're forming a circuit here where the electrons are moving down this wire, down to the negative electrode here, and you've got this circuit that is formed here because you've then got the positive electrode here, and again, the electrons are moving around the circuit. Remembering that what you're doing is you are using electricity to split a molecule. Okay, so you've got a molecule made up usually of 2 parts. It's either going to be molten, which means if it's solid, it's melted until it is liquid. Okay, so think about melting like metal to its liquid and runny, or it's going to be in solution, which means it's dissolved in water completely. All right, and that means that the ions that the compound is made of can move around. So having a look at this here, there's a few key bits here, the basics of this required practical. So when you have an ionic compound and it's melted or dissolved in water, so molten or in solution, the ions are free to move around the liquid or solution. And that's what this blue bit is here. It's the positive and negatively charged ions that are able to move around the solution. Now, these liquids and solutions are able to conduct electricity. And so we call this blue stuff down here the electrolyte. Okay. Now, with the electrolyte, what we do is with the DC, this current supply, okay, that allows you to pass an electric current through the electrolytes. And so the ions can now start to move, and they move towards the electrodes. Now, the positive ions that are in your electrolyte here go to the negative electrode. So the positive ions you can see in this diagram here have moved towards the negative electrode, which we call the cathode. They are reduced, which means they take on electrons. Remember, oil rig, oxidation is loss, reduction is gain. Okay, then you have the negative ions in the solution here, and they will move to the positive electrode, which is called the anode. Okay, that's this one on this side. That's why the negative electrons are here. These ions are oxidized. In other words, they lose electrons. So ions are then, the language we use, ions are discharged at the electrodes producing elements, and we call this electrolysis. So you usually end up with, and there's different patterns and nuances to this, but the positively charged, whatever's a positively charged particle in the solution or in the molten metal, you end up on the positive side here, and then you end up with a negative. Sometimes you get a gas produced at the negative, at the positive electrode as well. So here we call the negative electrode the cathode, and the positive electrode is called the anode. Okay. Right, so let's have a look here. When we're talking about energy, I said I was going to try and make this revision quick. In a reaction, energy is always conserved. It is never lost or gained. Okay, the law of conservation of energy in physics tells us that. Now, some reactions give out energy, which makes their surroundings warmer. So think about explosions. Explosions give out energy, or fires even give out energy. Around them, the surroundings get warmer. And X for explosions will help you remember exothermic reactions. Some reactions take in energy and they're the opposite. So they make the surroundings colder, okay? And they're the opposite of exothermic, which we call endothermic. Now, lastly, this is the very, very last slide. These diagrams from the last topic, which I think is the topic 5, these are called reaction profiles. And they tell us what type of reaction is happening. And you need to know the patterns for each of these. So you've got the potential energy up the side and the reaction progress going on across the bottom. So that's a reaction as it goes on. With the exothermic reaction, remember we're thinking about our explosion. We start off with our reactants at this particular energy level here. And what happens is those reactants that sit on this particular level of potential energy, they need to be given a certain amount of activation energy to get up this hill. And if you give them the activation energy to get up the hill, they can then roll down the hill and form products down here. And the products are lower than the reactants in terms of energy. And because the products are lower than the reactants, energy is given out, it's released, which is this red part here. You may be asked to do some calculations on a graph like this, okay, particularly at higher tier. That's your exothermic reaction. Energy is released or given out. Now, the endothermic reaction, same axes again, reactions going on and potential energy at the side. Your reactants are starting off at a lower level of energy than the products. Now, the reactants you can see have a much, much higher hill to overcome in order to form the products. And in this case, this is the energy taken in by the reaction. Okay, our activation energy is huge here, so the hill is huge. And the energy absorbed is this difference here between the product and the reactant. Okay, that's the energy taken in. This is the endothermic reaction. Remembering this tends to make the surroundings cooler, which is the opposite of the exothermic. Now, I hope that's helped with your revision for paper 1. It really was a whistle-stop tour. And so I'm hoping now you've got the key bits there. I wish you all the very best of luck for your exam. I'll keep my fingers crossed for you. Do let me know how you get on. I'd love to know how you get on. Okay, see you later.